Yes. Good morning, NDC. It's really cool to see so many here this early. And for one of my yet another modularization talk, I'm not sure if you got that from the title alone. It's a bit cryptic. I spent some time finding cool titles and then maybe become too cool so that people don't understand what it is. So I have to read the abstract, and the abstract is often too long. So yeah, sorry, I'm trying to improve on that. But what I'm talking today is about modularity, as I said. Again, I'm going to take a different spin. I spoke here a couple of years ago about modularity, and then I used the microservices in the title to lure people in, so I was better at title setting then. But I was essentially talking about modularity, but using domain-driven design. Today, actually, and I have another talk where I talk about business capabilities, same idea, finding ways to modularize your system. But I still find that we struggle with this modularity thing. And the problem is that modularity is sort of one of the big things that we can use to, in a way, manage complexity, if you like, right? If there's a huge domain, we want to split it up so we can work on separate components in separation from each other. But modularity is hard, and I'm sort of, yes, I have given these talks about techniques you can use, but I still find it's not, I find we're still chicken trying to find the corn, blind chicken trying to find the corn. Yeah, sometimes we manage to find it and it's all good, and there is some companies that really make this work, but most of the time I find that it's accidental often, almost. Okay, maybe a bleak picture, but I cannot find that. So at least for me personally, I took a step back and see modularity is not something that's unique to IT. That's been around for a long time. I mean, back in the ancient days. So I took a step back and see is there something we can learn from other disciplines on modularity. Sorry. Time for a timely drink. So I'm trying to, as I said, take a step back, see are there other disciplines we can learn from, how to do modularization, and specifically I'm going to look into system thinking. It's something that I've been really interested in the last couple of years, even before COVID. And specifically, I'm looking towards something as an area of system thinking called sociotechnical systems. How many have heard that term? Just to have a raise of hands. Okay, we are speaking a handful, so very few. It sounds cryptic. I'm going to come back to it later on, but it's really quite simple. It's social and technical together. You don't view them as separate. You view them together. So think of when you do analysis, don't look at the technical in isolation, also include the social aspects. That's basically what social technical is. Or at least it started like that. So we're going to spend some time on that. And I think it was Jeepo Hill who posted a tweet some time ago. He always said, I'm going to read it because it's a good tweet. And if I could retweet it a million times, I would, but I can only retweet once. So he said that software development is fundamentally a social technical enterprise. The strands are not separable in any way. Why is that? If you're thinking, so when you take the system thinking approach, you set yourself in a different viewpoint. You take a different framing of things. So social technical, then you see the whole system is then consisting of social aspects and technical aspects. And what we do as programmers or software developers, or even product developers or whatever, we are creating products. We are creating it. We are people creating it. We are creating it for people. And also what we write a code is supposed to be read by other people, right? So you collaborate. So if you take away the social aspects and sit again and focus on the technical, huge chunks of that system is gone when you do that. And I think when we do modularity, we focus too much on the technical and not ignore the social. I know we're talking about teams and all that stuff, but I still think we miss aspects of it. So that's what we're going to get into today. So why the proverb that I use there? There's a reason why I picked it, of course. I came to think of these things. I grew up in a rural area of Norway, the west coast. This photo was actually taken not far away from where I grew up. So I remember fondly these things, stone fences. People who come from the city probably don't have such relation to that. They've probably in the countryside, oh, that's pretty. Why do they build these silly things? But that's it. So people don't necessarily understand why they're there. But if you live in a more populated area, for example, you have a neighbor house. We always talk about neighbors talking across the picket fence, for example. The same idea. This is the same idea just for a farm, basically. So they're set in place for a purpose. And the purpose is not to keep people out, or even animals out. Most animals can jump these, apart from cows, we should try to keep in, for example. So there are certain animals that you want to try to keep out. But mainly you put them up so you know where's my farm ending and where's the next one starting. So you don't get into this infighting all the time. So that's the idea behind the sort of the proverb that good neighbors, fences make good neighbors. Actually, because you know where your area ends and where the other one starts, for example. And there's probably most Norwegians here, so there is something we call in Norway called allemannsrett. Okay, let's do a check then. How many knows of that? Everybody, basically. It's not a written law, but it feels like a written law. We, Scandinavians in general, expect to be able to roam around in the countryside freely. We're not going to be stopped by any, like these ones won't stop us. But if there were a fence, we would call the government immediately, saying, what stopped me from moving here? So we expect to be able to roam freely, basically. So allemannsrett means basically freedom to roam. So I see sort of when we put up boundaries, if we modularize a IT system, it's there for a purpose, but it's not to be like building a silo or a wall. It's about communication. You should open for communication across, and it shouldn't be a walled garden, if you like. And that, I came across this quote from this old gentleman. He's dead a long time ago now. Buckminster Fuller. He was an American architect and systems thinking designer and stuff like that. But he had a brilliant quote that caught my eye. You have to remember that any boundary is a usual fiction. So any boundary we put in place, not only are they designed, but they're also fictional. They don't exist, really. So when we put a boundary around one system or a boundary context on another, we design that. That is intentional for us. It doesn't really exist in real life. So we have all the power we have all the power to set those, to design those in the best optimal way. But I think we miss that a lot. We don't take that view and use it as a useful tool. We just put it in place and hopefully it works. And often it doesn't, I feel. So if the boundary thing is so hard, so why do we do it? I sort of alluded in the beginning that modularization is a really good tool to manage complexity, as I said. So is it worth doing this thing? I'm going to just run through a couple of slides. Oh, sorry. A little delay here. On why we do it. So now we're looking into, as I said, cross-discipline. So I'm looking into psychology. I'm not a psychologist, so if there's any psychologists in the room, please excuse my ignorance on this topic. But I'm going to try anyway. As I said, it's a way for us to manage complexity, but it's also to actually manage anything, work and life. We like to box things in. They even have a term in psychology called compartmentalization, right? You want to deal with one thing at a time. You want those to mix too much, because it stresses us and it makes us uncomfortable. So I just like this. It's a way of multitasking. My claim is that you really don't multitask, you just context switch a lot. Although I heard people claim that I can multitask. I think you automate one and then focus on the other. I don't think you can focus on more than one. I'm single-threaded, that's for sure. So next, why is this not? Whoop. Little there. I'm not going to go too much into this, because this is a huge area in psychology called cognitive load theory. And John Sweller is probably mostly known for it. But his approach is, or the main message there is that our cognitive load is limited. There's such a limit how much you can keep in your head at the same time. It's basically the memory limit of your head. And that is surprisingly limited, actually. So we have sort of, during your evolution, created techniques to handle that limitation. So he lists 3 types. One is I should have my glasses. Intrinsic cognitive load, that is sort of, that's just you understanding what you're looking at the moment. So if you're analyzing anything, that's sort of your intrinsic load. You can't ignore it. The extraneous cognitive load is something that is put on For example, stressful doing a presentation, that's that. Or even worse, when I did online presentations, because all the technical things, I've had technical issues just before I went on now. That's the extraneous load. You don't need that. That's just bothering you. And the most curious one is the next one, is that, and that one you don't want to limit, the germane cognitive load. That is what you want to increase. So that is when you think of biases, when you have a mental model and you see something new, and you try to map the new one into your mental model, then you're trying to maximize that. And that's a trap, of course, in a lot of situations. Right? That's why we have biases and stuff. Modularity doesn't deal with extraneous, of course, but it deals with intrinsic, because you limit your sort of the area that you're looking at. And it also increases the forgot the name now, the germane cognitive load, because you are familiar with that area already, right? So when you get new stuff in and you're going to make some changes to it, you kind of know where you want to go with this, right? So your mental model is there. By the way, those of you who know team topologies, they write about this in this book. So they take it not from a personal level, but actually lift it to the team level. So the team has a maximal cognitive load, is their idea. So that's the first part. So the first argument for modularity is just to manage complexity, basically. Right? So the second I want to get into is scaling an organization. If you want to have, say if you're a small startup, sure, you have one team. You don't have to modularize necessarily. By the way, just to get out on the table, I forgot in the introduction. When I say modularization, I'm not talking microservices. Just to get that out there. Microservices is one way, but modularity is a lot more than that. It can just be mental models even. So just to bear that in mind. So don't go run into that microservice, one team, microservices and all that stuff. That's not the same. It's not what I'm going into today anyway. So say if you have a startup, one team, fine. If you're growing, you need to scale up. And you don't want to have a team of 20, 30, 40, 50, 100,000 people. You have to split it up. That's natural, right? It fragments. And then you want to have these teams. And do you want teams or do you want work groups? I distinguish between the two. I see other people do as well. Work groups are people that are working on the same system, but are working on different things. So like a stand-up wouldn't make sense, for example, because they are not working on the same thing at all. So, for example, that's just an indication of their work group instead of a team. A team has a common goal, for example. There's something they want to reach together. They have a purpose. So we want to find the right boundaries for the teams. Tricky. And there's another, and sort of this is a core learning for sociotechnical, which is actually, sociotechnical is one thing, but there is a branch called sociotechnical system theory, which makes it even more abstract and foreign. But just bear with me, just ignore the system theory a bit for now. But the idea is that you should have a team that has a whole task. There shouldn't be at least as little as possible interaction between teams. There shouldn't be unnecessary coordination between teams. There will always be some, I must stress that. We're going to go back, that's going to be obvious later when we get really into system thinking. Because teams that are, that's why I hate autonomous teams alone. Because an autonomous team wouldn't have any lines between them. They would just go out and do whatever they want. And we're going to see that later. Then that means that they're not part of the system anymore. But we'll go back to that later on. So there's always some. Nobody's an island, right? Yeah, and the whole task thing, if they're going to be able to have a whole task, they have to own everything regarding that task. They have to own the data. They have to own the tools that they need to use, and they have to own the processes. Right. Okay, this is an idealist picture, but you can get there, actually, if you do this properly. Yeah. Of course, the other one, this one I've used before on every talk, I believe. The idea that there is a time to market, there's a wish from the business to get a faster time to market. So when I say need for speed, it's not a need for speed, you have to type faster, or we have to get the story points faster through the pipeline and stuff like that. It's not that. It's getting stuff into the market as soon as possible. And what, for example, the teams does, semi-autonomous teams. Okay, I introduced the term a little bit earlier, but you notice the lines between the teams, so they're not autonomous, they're semi-autonomous is the term I use at least. So when you have this separation like I showed earlier, you can parallelize work People can work in parallel. You don't have to. You remove the unnecessary bottlenecks. So that means that your business can go faster. So it's not typing faster; it's getting rid of the waste, if you like. But there's always a but. This is probably a situation that many of you are in. I hope not, but I've been for a lot of my work. You know what's coming. It's a mud thing, right? I didn't find a good picture of a big ball of mud, so I used this. But from the paper, there's actually a paper called Big Ball of Mud by Foot and Yoder. And I love this quote. I recognize that. So sadly, architecture has been undervalued for so long that many engineers regard the life with a big mud as natural, normal. All right. Okay, this is just how it is. We don't know any better. When I started in my career in actually doing real programming in early 2000s, I worked on a monolith. That was the world I was used to. We were actually proud how many code lines we had. I think we had a presentation on Java almost. This is a Java one, so sorry, I'm a Java background, so you can hate me for that, but I hope you're inclusive. But we had a presentation on Java Zone where we actually bragged about how many million lines of code it had. Things have changed since mid-2000s, luckily, happily. So, yeah, so of course, the next bit then about modularization is to get rid of that monolith, big ball of mud, obviously. But the coordination cost that I mentioned earlier between teams, here you want to remove the coordination cost as well, but it's the technical one you want to remove. How many have read this book? Now I want really see many hands. Oh no, go get it. It's one of the best books you can get. It is such a huge investment. Do get it. Because we have actually data on this now. Of course, you probably have heard about the DORA metrics. And you want to see how fast you can get stuff in production and how fast you can react to errors in production and all that. So they are sort of the people, the DORA research was behind these 4 metrics. I don't remember all of them. But this quote is also from the book. I can read it. As a loosely coupled, well-encapsulated architecture is the biggest, I repeat, biggest contributor to IT performance, even larger than test and deployment automation. And that's not just something they said. That's from research, right? Quite detailed research as well. Yeah, it's not correlative, but sorry, causal necessarily, but it's a huge survey. So I think the numbers are good. And that is, I mean, I repeat, that is from the people who came up with the DORA metrics. It says in the book that it's actually this is more important. There's also some research, again, sociotechnical. I just came across this quite recently. There's something called, another academic term, because these are academics, of course, sociotechnical congruence. It's a tricky one. But the idea there is that the work task that the team has should be aligned with the technical, or the need for integration, or the communication. So the communication should happen within a team, not across the teams, for example. Then you have sociotechnical congruence. They are aligned. If you have, for example, a big ball of mud, you have to talk with everybody. Every team has to talk with everybody. You're not socially congruent. Those of you who have heard of Conway's law, it's the same space, basically. There's also something called mirroring, which is a generalization of Conway's law, by the way. By the way, that one of the papers on sociotechnical congruence, they show that if you get this right, if you get this team right, you actually reduce the resolution time by 32%. So it's quite considerable. So don't ignore this part. I'm not going to go quickly on this, but there's actually more research. This is not from another discipline necessarily. This is also, I mean, Accelerate was us basically doing research. This is from Kalis Baldwin. She's coming from economics originally, and she's looking into more, not IT necessarily, but whole companies and how they react. And she said, and she's really into that real options idea, that when you modularize, you get an increasing number of options that you can go to. So if you have one monolith, there's only one way you can go. If you have a lot of modules, you have a lot of options, right? So I don't think I have the coder. No, I forgot to include that. But she said that it's the recombination, I think, that is the new gold, so to speak. It's the way of, if you have a lot of modules, you can recombine it. Okay, it sounds like the old SOA idea, but it's there, and there's hard research on it. At least they create options. You don't force it into one. Oops. There's lag. Oh, here's the quote, by the way. Experimentation and recombination is the new game with IT, he says. Because IT is enabled to do that modularization in a good way, if we do it right. And this is just a thought experiment, though. But if you have 25 number of modules, and you have 25 number of experiments you want to run, you get 25 times the value out of it. And yeah, of course, this is a thought experiment, and she said you don't include cost for modularization, or cost for integration, or experiments, or anything, or testing. But she said, but the value multiple of 25 will pay for a lot of engineering costs. So there's that. So don't ignore that aspect of modularization. So let's get into system thinking. I'm starting with, this is probably, I think I got this from Dave Snowden. He talks about complexity. And one example he used for complexity is children's party. For everyone who has kids at home, a birthday party at home, can relate to that. You can have all the plans in the world. When the kids enter the house, it's gone. It's basically mayhem. You try to restrict and have some enforcement there and there, but you have to manage, right? There's a huge complexity there. And we're talking about there's people even, and there's kids, and they do any crazy thing, right? My angle is, it's curious how we can manage to do those things, but somehow we can't manage the complexity in a work lab. In work lab, we have to force things into boxes, and we have to think linearly. We have project plans and predictions and crazy stuff, right? Suddenly, no, we can't deal with complexity. We have to remove every sign of it. So we try to order stuff. You make it predictable. And I think that maybe my hypothesis is that at least I come from STEM, from physics, astrophysics actually. But most of us probably come from that STEM background. And there we drilled into these ideas. We should get rid of an environment. I mean, even if I'm going back to, yeah, that's the next slide. I can just skip to that now. In physics, I love this one. I'll give you a couple of minutes to see it. Notice what the title is. What makes sand soft is the title of that drawing, Mexico City. And my specialty wasn't quite quantum mechanics, but I was into general relativity when I did my thesis at university. I thought, oh, this is so complex. This is so cool. I'm working on the edge, bleeding edge, and cool stuff. But what I see, this is quite ordered. Physics is surprisingly ordered. If you think about the theory of, the laws of thermodynamics, all heard of that, so increasing entropy, conservation of energy, and all that stuff. If you read it, if you go into it and read about it, it says there is some hard restrictions on that. It has to be a closed system. And closed means nothing goes in and nothing goes out of that system. It's closed. So it's an idealist view of things. And a lot of physics, unfortunately, is that. We want to go for those beautiful models that we have. And then there's even a heuristic that an equation should look beautiful. That is one of the characteristics of physics. I'm not taunting physics. They're doing a great work on all that. But they simplify stuff. They make simplifying assumptions in order to make the theory beautiful and make it universal. So they take away the environment completely. Like free-falling objects, there's an important word there, free-falling. On Earth, they don't free-fall. So the idea with the hammer and the feather, for example, they did the experiment on the moon. You can show it worked there. But it's an idealist situation. It's not a common, it's not what we usually deal with. For example, finding out why sand feels soft and not hard, because it's rocks and should be hard, right? Yeah, I'm going to skip that. So am I on time here? Okay, hopefully I won't run long. The general consensus is that, okay, modularity works. This is something that we want to go for. We even have data, as I showed. And we tried it for ages. But if still, as I said, I think we still struggle. This quote from Ruth Malan is really, I mean, it shows what we can look for and what sort of area we can sort of investigate. I can read it out. Architectural design is system design. So there you have a clue already. System design is contextual design. Right? You can't have general systems. They are specific. It's inherently about boundaries, again, to that modularity thing. What is in, what is out, what spans, what moves between, and about trade-offs. It reshapes what's outside and what is inside. So, there's a tip here for us to venture into it. I'm not sure if there was this quote that brought me into this rabbit hole of system thinking. It might have been somewhere else, but this definitely was like a aha moment when I saw that. That's a really good description. So architecture, system design, basically the same thing. So yeah, so this is hard. So let's go into system thinking then. Let's try to system thinking 101. I'm not going to go into all ugly details, but try to keep it at a hopefully understandable level. So yeah, this talk is very theoretical, as you probably understood by now. You can leave if it gets too much. That's fine. I won't be offended. But I think we need that theoretical background because if we're going to understand what we're doing, we need a framing. We need a theory of why we're doing what we're doing. There was also a quote the other day, by someone saying, "Oh, I'm just an action man. I'm just doing stuff." But what you're doing, if you're just doing stuff, you have a hypothesis in your head, but you have automated it. So you're running on automation. And you're probably going to want to repeat the stuff that you did before, that worked before, you're just going to do it again. That's what we're doing. So you don't create a mental model. There's no theory behind what you're doing. And I think system thinking can help us, at least give us a different framing on that. So I saw a definition of modularity somewhere. I don't know where, but I've added it to the slide notes, apparently. Modularity is a system decomposed into semi-independent parts hidden behind abstracted interfaces. Again, the semi part, right? It's semi-independent. And that is, again, a clue. Yeah. So I used cogs here to illustrate a system. Based on that picture I had with those kids at the party, and I probably already said it, what's the problem? And somebody want to venture into why this illustration is actually wrong? Anyone? Yes?
Can they actually move?
They move, yes, they can move, of course. That's the, yeah.
At the same speed?
Sorry?
At the same speed?
Yes. It's very ordered, right? It's very predictable. When you turn that, you can easily see what's going to happen to the green one, for example. So it's very ordered. And this is I think that's one of the main problems we have. We think with a machine model in our head when we make stuff. When we program, we're creating a system that is machine-like, because we want the machine to do what we tell it to do. So basically, it is a machine we're creating. And that's very ordered. But the environment that we are creating the ordered system for is definitely not ordered. We're going to go back to that, of course. So, there is the reason why I showed, not just to show that it's wrong, but also there's something interesting here. The part fits, that's one thing, right? And they're definitely interconnected. Everything is connected to everything in a system. If one part is not connected, if there is a cog here that's not connected to the other one, it's not part of the system anymore. It's outside. It's a system of its own. So that's an important distinction now. Yeah, so the machine model. So in a machine model, the whole is the same as the sum of the parts. Right? You can just sum up these cogs and you know what the whole is. But the thing about systems, really, if you really go into it, the idea is that the sum of the whole is larger than the whole is larger than the sum of its parts. That's where we want to get at, and that is what a system really is. Not if you go beyond the machine model. That is. Yeah. So one thing is they fit, but we all know parts can change. What happened to the system when one part changes? It's for the one team. We're going to stop doing that soap thing. Okay, it brings me back to the 2000. But okay, we have a team. They have soap APIs. The other one, no, we don't do it. We're on a REST everywhere now. Or no, we're going to RPCs that's old school. We're going to do events now everywhere. Or one team, now we're going to be product teams, proper product teams. So we're not going to the project stuff. Ignore, right? So the parts change. And that changes the whole idea of our system, right? We can't have, there's no predictability when things change ad hoc. And especially if there are humans in the parts, we change all the time, from day to day even. And we change it. So this creates a whole lot of local uncertainty in the system. And as this shows, local optimization, bad idea. I think it was Russel Lacov who said that if you optimize every part, if you're lucky, the system doesn't get worse. Even if all the parts are perfect, he has the illustration of a car. If you pull all the best parts from every car in the world and put them in a room and try to reassemble it, is it going to work? No, of course not. They're not going to fit. So, yeah. So just a quick definition of a system. I'm going to use Russel Lacov, as I believe I mentioned earlier. He has a definition. He said that a system is as a whole that consists of two or more parts. And they have to satisfy three conditions. It's from one of his books, I believe. The behavior of each element will affect the whole. So in that sense, the illustration works, right? Every part affects the whole. The behavior of the elements and the effect it has on the whole are interdependent. Again, the parts are dependent on each other. But not only that, they are dependent on each other, and that dependency also has effect on the whole. So everything connects with everything, basically. And he also says you can't create isolated subgroups. That's a third criteria. So if we have another system there, which is within the other one, if it's part of a system, it's not separate. It's there. It's not. If it was separate, it's a different system, as I said. If you take a Coke out, it's a different system. So inherently, and also that means that systems are hierarchical. It goes all the way, turtles all the way down, kind of thing. Yeah. So there's a famous quote by Lacov where he says, "A system is never the sum of its parts; it's the product of its interactions," which is a beautiful, concise little quote. It takes a lot of time to get that, sink that in. But so we're not going to try that here, but yeah, you can look it up. It's really, really profound. Another definition of a system is by this woman, Donella Meadows. Anyone know of her? Read the book? A Primer of System Thinking is probably a book that I only see 2-3 hands. She worked on she's a system thinker, basically. We can leave it at that. But she has a different definition of a system. She said that a system, a set of interrelated elements organized to serve a particular function or to seek a particular goal. So then we bring in, the system is not there for its own sake. It's there because it wants something. There is a purposefulness of systems. Right? And if you go to Lacov here again, he actually distinguishes between different types of systems based on that purposefulness. He says if you have a system consisting of parts and a whole, of course, if you have a deterministic system, there's no purpose for any of them, either the whole or the parts. Like a car doesn't have a purpose on its own. Or the carburetor or the engine doesn't have a purpose on its own. It has functions, yes, of course, but it doesn't have a purpose. The car doesn't say, today I want to go, okay, one day maybe we have cars that do that. But as of now, we don't, right? So it doesn't really have a purpose. And I believe when we get there, the car that's self-driving, it's we who control the algorithms, still it's mechanistic or deterministic. The second one is animated. And now we're moving into us as systems. So animated system, there the whole has a purpose, but the parts doesn't. So you as a human, yes, of course, I hope you have purposes. You have something that you want out of life and stuff, even at work, I hope. But your heart and your lungs doesn't have a purpose. They have functions in your body, but they are there for the whole. That's the distinction he makes. And then he moves one level up to the social systems. And now we're getting into the social technical idea, right? The social part of that social technical. Because the social system, the parts you have in your team, you have a purpose, and the team hopefully have a purpose as well. A work group may not have a purpose, by the way, but a team sure, probably should. And there's also go another level to ecological. That is sort of just to make it complete, where sort of the parts have purposes, but the whole necessarily doesn't have a purpose. Like a humankind doesn't have a purpose. If we agreed on something, maybe we would. Fighting climate change, maybe, but we don't see to be good at that. So I think it's right on that level. So if you go back to this model, the parts have people in it. And that changes the picture even more than I said earlier, with the interconnectedness and all that stuff. Because the purposefulness of those people are enormous and they're varied. The larger team you have, the more purpose differentiation you have. So again, back to my argument initially, is that if we ignore these parts, how can we create a modular system if we ignore the purposefulness of the parts? We don't know what the part is for, even if you don't consider that. So we're moving into an area called, this is basically social technical system thinking. Is how can we view this the social and the technical together? There is an extension to to social technical system design called open system thinking. Again, even more academic. But the idea is that any system is open. It's affected by its environment. The environment is always there. You can't take it away. So back to what I said about physics. Physics is a simplification. So so the general idea is that every system is open, but sometimes we can restrain it, make it close for our purposes. For example, physics to get general cool laws or whatever it is. Right? So by default, systems are open, is the idea in that theory. This is actually a picture of the guy, Russel Lacov. I didn't introduce him. He's one of the main system thinkers, a very great educator. Look up some of his videos on YouTube. They're excellent. He has an excellent way to explain how things work, especially systems. Like the car analogy I had earlier with putting parts together on that, that's from him. So I've watched video hours and hours on Lacov sitting on stage just talking. It's fantastic. But anyway, this quote is really good, and that also gives us another insight. It's a system is more than sum of parts. He already said that. It's a product of interaction. It's an indivisible whole. And the second sentence is really interesting. It loses its essential properties when it's taken apart. So if you have a company, for example, that's a system, right? We agree on that. Hopefully I agree on that. If you take a team, or you take a system or an IT system, and you look at that in isolation, you're not seeing the whole. You're losing a lot of its essential properties by doing that. You don't seeing the whole. You don't see in the sense that Lacov was talking about here. Which means that the tool I've used all my life is actually not sufficient. Analysis. We all do analysis. Oh, we have to analyze this and this and that. We all do. I've been told to do that. You be good at analysis. Analysis is necessary, but it's not sufficient. It's something that system thinking tells us. So actually, Lacov called it reductionism. That's another academic term. But the idea is that you decompose a system, explain the parts, and based on explaining on the part, you understand the whole. That's analysis. So there is a one-way direction, right? But Lacov said that you need synthesis as well. And what that is actually the reverse of analysis. What you do then is take one step up. If you're looking at an IT system, you need to take one step up. What is that the IT system part of? Of course, the organization, but it's also maybe relation to other systems. So you need to one step up to understand its relation to everything else. And when you understand that, then you can go down and do analysis. So what he's saying is that actually what you don't want to do is when you put things together, what you're looking at, you explain how it works together, and then you dig in and explain the parts. Go up, wide, then down, basically. But up, look at that, the system that you want to look at, and maybe even go further down. Which means at least when I've been working as an architect for quite some years now, and that insight has brought the context, the understanding for me why I can't just sit in a team and discuss how we're going to solve this. I have to take a step up and see how will this affect everybody else in the organization. I have to do that. So this has become a sort of a working process for me now. I never look at the isolation, always go up. Okay, if we do this, yeah, if we switch to events instead of RPC, how will that affect the other teams? How can we coordinate with them? How would it affect the business processes? How would it affect the business ability to make changes to the system? I mean, you have to go. How far you want to go? You probably don't want to go to the universe level. So we have to stop somewhere. So probably organization is a good way to stop. Yeah, so how can you find this? I'm not going to spend too much time on that because I've talked too much about the fun thing, which is system thinking for me today. But how can you find decent candidates? I'm going to help you a little bit to give you some hints there, though. I love this illustration just to show you that there are actually some indications of boundaries in systems. This is, of course, geological faults. You can see there's clear boundaries between things. So this is what some people call natural seams. Look for the natural seams in your system. Look for the sharing layer. This is basically sharing layers, right? I think it's Michael Feathers who talked about natural seams, by the way. I think Team Topologies talked about fracture planes. So just look at where things change from one to the other. That's where we want to look. Sorry for whiteness. I see people blinded by the... I should probably stop using white slides, by the way. Look at social system first. We all remember January 6th. What was happening in America then was factions, political factions. Like people getting together, getting somewhat crazy ideas, and then acting on it. So a social system will fracture if it's large enough. Like I mentioned also, if you have a company, if you have a small startup, fine, it won't fracture. If you get, say, above 20 or something, it will fracture naturally. People will join the people that are like-minded and, okay, oh, you like that tech, let's talk, like stuff like that. So I think, and this is where Team Topology comes in, because they take that in as an active way of finding the boundaries, actually, because they're setting up what I call attractors. These are the teams, right? So they say, we're going to have a platform team, for example. If you're interested in working on tech, come to us. An attractor, right? If you want to work on business problems and want to talk to customers and all that, yeah, maybe then Streamline Teams is a good thing for you, right? So you see there are attractors there that can help actually fracture the system by setting up these attractors. So that's actually one way you can do this. But it's probably not, you can't do this alone, obviously alone. If you go way back, as I said, modularity is nothing new. This is probably the first in IT, I believe, was the Panas. He wrote this paper in 71, I believe. I think this version is for 72. Again, text slide, but just the title. On the criteria are to be used for decomposing systems into models. Sounds like a perfect paper to start with, right? Yeah. I could probably use that title for this presentation. But what he says that the paper discusses modularization as a mechanism for improving the flexibility and comprehensibility of a system while allowing the shortening of its development time. Basically what I said in the introduction. He says it in one sentence. I used several slides, but he's more smart than me probably then. But the next sentence is interesting. The effectiveness of modularization is dependent upon the criteria used to dividing the system into models, which means that you have to be conscious about how you do this modularization. In this paper, he has an example of creating an index, I believe, and he used functional splitting up into functional steps. And he shows explicitly in the paper that that doesn't work. Because you have one minor change to one will affect all the others. It's shotgun surgery, basically. So I think that's, if it's there where this functional decomposition anti-pattern arises, I'm not sure. But what his idea was, we propose instead that one begins with the difficult design decisions, or design decisions which is likely to change, and isolate those. This is information hiding. I'm not going to go further into that. If you want a good talk on information hiding, Sam Newman has some really good ones on that. But you probably recognize this pattern because this is what later led to object orientation, for example, and stuff like that, right? Creating objects that are encapsulating information. One issue with this, I like this approach, of course, but it's a bottom-up. It's an emergent thing. You have to touch the system. You have to try it. You have to sort of modularize it and try what works, and then probably readjust it. And yeah, so it's an emergent, I would call emergent way of modularizing a system. And quick on that. This is from Foot and Euros' Big Mall of Mud again. They use the analogy of a house, and the idea is that look at things that change more frequently than others. So, for example, the foundation of a house doesn't change much, I hope. The structure of a house really ought to change less than the foundation. The outside of the house, I had to change some rot this summer, change some boards. That changed more frequently, and then you got more frequently the more in you get on a house. So their idea is that look at, so this is from Brand's How Building Learn, by the way, as a book. So if you look in our industry, it could be like data versus code. Data changes often. Code not that often, for example. There is the parts of code that change more often than others. Some is more stable, more probably a utility or something like that, doesn't change that often. There's implementation and interfaces. Interfaces is stable, implementation can change. So that's the sharing layers they're looking for, is what change frequently or not. I'm not terribly fond of that, because it leads to layering, I think. And the old bimodal IT, we have back-end system, they changed rarely, and front-end is going to be, they're going to change a lot and be the fans. So you have all the cool developers in front and this sad old gits in the back. And I think that's problematic, because again, that's, you divide the system in an unnatural way. I think it is a way to separate the system. I don't think it's the best one, though. And I think we have learned that so far. But it's also emergent, by the way. So this is bottom up. You start with code and then see what's, you're finding your way. You're crossing the river by feeling the stones, basically. But I think we need something more. We need something that is top-down. And the top-down thing is, it's not top-down. Is we need some architect that sits in the ivory tower and that's that's not top-down. That's what I'm saying here. Top-down is taking again back to the system thinking, taking one step up, seeing the whole. That is top-down. Taking an outside-in view, I actually use instead of top-down or frequently, because I don't like the top-down thing. Just to illustrate that point. I don't know if people are probably familiar with Name of the Rose. It's one of my favorite books of all time. There was a TV series, came, how long was it? 2019, British. And that TV series, these are the two monks, but they are the main characters in the book. It's very close to the writing of the book. So there's a quote from that book, which I heard when I saw the minutes. Oh, this is so perfect, I had to bring it in, because it illustrates the problem I think we have very well. I'm going to read it, of course. Oh, again? Lagging. I'm not going to read it for you, of course. Thus, okay, just setting, don't start reading it, just listen to me first. The setting is that these monks, they're trying to find a hidden room in a library. And the library is a maze, and they can't find a way. So then, William here, the main character, has a brilliant idea. He says that they have to go outside the library to look it from the outside and figure out where are the rooms and where could the hidden room be, basically looking on from the structure from the outside. And he used this analogy. Of course, it's a clergy, so it's God involved. Thus, God knows the world because he conceived it in his mind, as from the outside, before it was created. And we do not know its rules, because we live inside it, having it found already made. This reminds me of when I was stuck in that monolith years ago. I only saw that part. I didn't see all the rest. Right? Because I didn't know him, but nobody discussed talking to somebody else in the organization. Just keep what you're doing. So I think we need the outside-in view as well. There's a lot of techniques for doing that. I think I alluded to some of them earlier, because I had talks on that. This is on business capabilities. Oh my God. Sorry. Just a quick teaser on business capabilities. You can look at my talk. I have some blog posts on this as well. But the idea is that for our business capability that is something that the ability that the business wants to have, either to meet its customers or to support in internal functions or whatever it is. It's an ability to do something. That's a business capability. So this is from Ulrich Hohmann. He said a business capability is a particular ability or capacity that a business may possess or exchange to achieve a specific purpose or outcome. Again, back to purposes and outcomes. So it all ties together here nicely. Since this is a .NET conference, you probably know this guy, Judith Hahn, Service Bus guy. He's really into service orientation. He has a different spin on service orientation, I feel, at least from what was happening in the mid-2000s. So he's connecting the capabilities to the services. He's saying that the service should be sort of a technical authority for their business capability. So if you imagine you have a huge company and there is a business functions there, then that service serves that business function. So it's not microservices there. They're quite large, basically. So that's one way to look at the business, what capabilities do we have, and then decompose and create a system based on that. That's one approach. Just to give some examples how this could look. This is a nested hierarchy. So you have, for example, on the top level, you have some corporate management, you have product development, you have delivery, support services, market development, and some oversight, or II, or sorry, business intelligence. And then you can break down the market development into another level of business capabilities. Here's like contract management, direct marketing. Yeah, you get the idea, right? So this is a nested hierarchy. And you can base these. Maybe these can be good modules for you to start. So maybe you have a team that do direct marketing, for example, and they have IT support systems for that. So they have IT in there. So there's no separate IT systems in this model, by the way. IT is all part of the whole thing. Where is IT needed? IT people are there in those teams, if you like. The other one I want to just quick mention is, of course, domain-driven design. I have a lot of involvement in that community, so I love domain-driven design. So this is something that came out, a good thing that came out of COVID. It's like somebody got together, something they call DDD crew, kind of fancy name. They came together to say, what sort of starting process can we sort of define so people get easier entry to domain-driven design? And this looks very ordered. There's 1, 2, 3, 4, so it looks like steps, and people get, of course, hung up in that. Oh, we have to do one first, and then we have to do, like, so it's got a waterfall again. So they changed the illustration to iterations and stuff. But I think this works as long as you are aware of that iteration part of it. So here you go up, like you understand the business needs first. So you have to align the business model and then user needs. And then you start to discover domain, digging into it. There's a lot of collaborative modeling done, for example, in domain design, like Windstorming, that you probably heard of. Or if you enter that domain storytelling talk yesterday by Henning, perfect. And then you decompose based on that. So again, you take the outside, you look at the whole, and then you start decomposing. You don't decompose before you have seen the whole. The same idea. Of course, domain-driven design is very fond of linguistics, so the linguistic is guiding the vision between the components. I love this illustration of a bounded context there, where you can see one word can have different meanings in different contexts. Like in the culinary bounded context, the tomato is a vegetable. In the botanic bounded context, it's a fruit. And in the entertainment industry, it's you see what it is. So that means that things have different contexts based on its wording. The wording can be the same, the item can be the same, but it's a different meaning in different contexts. That is essentially domain-driven design. And a brilliant technique, as I mentioned, is the Windstorming. This illustrated here with Alberto Brandolini himself, the master of Windstorming. He came up with it. I think it was Dan North who said, "Eventstorm everything." So this is a wonderful technique. It's super simple. You just get a lot of stickies, specific colors. So he's strict about the coloring. So it has to be orange stickies for events, and then you just create a timeline with a lot of events happening, business events that are happening in that. And then you can start to see where things groups. Where some events are grouped together, and there's one event alone that triggers a lot of other events. Or when people are doing the modeling, a lot of people group around certain parts of the board, while other people group around other parts of the board. And by that, you can start seeing the emergence of the boundaries. This is another great technique. I'm going to skip that because I got 5 minutes left. I promise not to run late. I'm going to skip that too. Just a quick note on that. That was from Henning's. This is from Henning's talk yesterday. So it's just to see how fresh I am, my slides. But here shows that the domain storing technique can also be used to find the boundaries. Because you look at the processes and you see which processes are tightly connected to each other and group it based on that. So this is not, as you see, this is not information hiding. This is not about trying to figure out what changes frequently. So this is about processes and big things that you use to illustrate. If you want, by the way, just a little tip. It's a free book. I recommend you to get. If you're interested in all this type of collaboration techniques, this is a free book on Lippert. Of course, if you pay, you give to charity. There's a great chapter on event storming. There's domain storytelling there. I have 2 chapters, one on user story mapping and one on business capability mapping. So just a tip if you want to get into more of this stuff. Yeah, so I'm going to sort of wrap up now. So I think bottom up, like information hiding and all that stuff, can work, but we need to take a bigger picture. Because if we don't, and I think that's back to the chicken and finding grains, I think when we modularize, I think my mental image is more like this. It's kind of accidental, and I think we break stuff a lot when we do it. Because we don't see the whole, and we optimize for some parts, and then the rest, another part is ruined by what changes in one part, for example. So the system as a whole is basically can end up being broken, like a pane of glass. So if you do microservices, that's even worse, because then you put a network in between. So yeah, we all know this with the monolith and all that. Yeah. I promise not to mention microservices too often. I think twice. So what I think, to cope with complexity, modularization is a great tool. And in order to do that, we need to join our forces. So different viewpoints from everybody. Some has probably even the ivory tower architect can have some important role in this, but it's not a sole role. It's something that he or she does together with everybody else. Even the manager, even the CIO could have some ideas about this. So we should do it collaboratively. That is the main takeaway, I think, about doing this. And taking the outset, take one step up and seeing it together as a whole. So just like an opposite of the broken pane glass, I want something as beautiful as this. So my advice is to take the holistic view and do what Lacov said. We should do both analysis and synthesis. So when you are given a task, can you analyze this change request or this initiative? Yes, I can do that, but I have to do synthesis as well. If you take this from this presentation, I'm happy. Because then you have sort of grasped a core idea here, that you have to see the parts' relation to everything else. Not just the things beside you, but also above you or in the containing whole. So there's another great quote from Lacov. I have a lot of those. As I said, he's brilliantly at this. It's, analysis yields knowledge, like you understand stuff when you do that. Synthesis yields understanding. You understand why it's supposed to be the way it is. So do both. Do both. So just to summarize, 2 minutes left. I think we need to leave that machine age. So the illustration I used, just remember that COGS, wrong. It's a usual model, but it's wrong. Because what we're working in is not mechanical system. It's not deterministic system, as Lacov said. We are working in social systems. We have some tech in it, ergo social technical systems. So maybe social technical is not as foreign now that you see those. Hopefully it isn't. So I think yeah, so what we need then is we have to have more modularization with semi-autonomous teams owning the whole task. If you get there, you're in a good place. Then you have important modularization that works somehow, because you have this isolation between the parts. So, and you have to also remember, you don't get one, there isn't a model out there waiting for you. Like, there is a perfect solution to this. We get there, the nirvana, it's going to be perfect when we get there. I can guarantee you when you get there, things have changed so much that it doesn't fit anymore. So you have to adjust continuously. So even if you find a good model here, be aware that you probably should change, or at least have the capability to change frequently and resolute when you need to. So which is a bit of a bummer, basically, because you have to spend all your time creating this perfect model. So don't fall in love with your models, people. Yes, and with that, I'm going to thank you very much for your attention. I'm actually right on time, so we don't have time for questions, but please contact me on Twitter, for example, or you can come here if you like. Or I'm going to be at a Russel conference, but thank you.